Software has bugs. It seems unavoidable. The most common ways of finding bugs are testing and code reviews. But as all users know, software nevertheless ships with bugs still unfixed. In fact, many of these bugs are known to the developers, but they were not deemed important enough to fix prior to shipping. Many other bugs are not known. Why are they not found? It could be that the bug is in a rarely used feature, for example, in a device driver for a rare piece of hardware. Or the bug arises in rare circumstances, for example, when memory is nearly exhausted. Or the bug could arise non-deterministically. The circumstances that make the bug manifest could be unpredictable, and thus make the bug hard to reproduce and hard to fix.
One way we can try to find those bugs that testing misses is to use static analysis. And this conceptually makes sense because static analysis can consider all possible runs of the program, perhaps even those that are rare, non-deterministic, and so on. We can feel heartened by the explosion of interesting ideas and tools that are being considered in research, and by the fact that companies are now selling and using static analysis tools. So there's great potential here to improve software quality. The question, though, is can static analysis find deep, difficult bugs? So in principle, yes, but maybe in practice, not so often. Okay, why is this? Well, it's because commercial viability implies that you have to deal with developer confusion, false positives, error management, that is, quite a lot of code that has nothing to do with the core idea of analysis itself, but rather the way that humans use the analysis. One particular thing that companies seem to do is to keep the false positive rate down. They do this by purposely missing bugs to keep the analysis simpler. This turns out to be a good idea because studies show that developers get tired of dealing with alarms that don't turn out to be true bugs. And they're not interested in sifting through, say, 9 alarms, even if on the 10th time they find a really important bug. So companies respond to this, and they make tools that will miss bugs. So one of the issues here that makes false alarms hard to deal with is abstraction. Abstraction is critical for static analysis because it allows us to simplify our view of what the program does so that we can efficiently enough model all possible runs. But to do this, we have to introduce conservatism. Now, the various sensitivities, like flow, context, and path sensitivity, add precision, so that reduces conservatism. But these more precise abstractions are more expensive, which means that they won't be applicable to larger code bases, at least not at short timescales, and they still will not completely eliminate the false alarms problem. One particular problem that makes false alarms hard to deal with is that the static analysis technique may use an abstraction that is not familiar to the developer. That is, the developer is not able to make sense of the alarm that the tool produces because it was produced in a way that the developer can't relate to and therefore can't easily triage to determine whether the bug is true or not. So for the remainder of this unit, I'm going to talk about a technique called symbolic execution that's kind of a middle ground between testing and static analysis and aims to retain the best features of both techniques. We start with the observation that testing works. Reported bugs are real bugs. The problem is that each test only explores one possible execution of a program. If we do assert f of 3 is equal to 5, well, we've checked that f of 3 is equal to 5, but not that f applied to other input values also equals whatever it is they're supposed to equal. In short, tests are complete, but they're not sound. And while we hope they generalize, they don't provide any guarantees. Now, symbolic execution aims to generalize testing. In a sense, it's more sound than testing. So we can write tests like this. We can say that y is equal to alpha, which represents an unknown or symbolic value, and then we can assert that f of y is equal to 2 times y minus 1. This is basically saying for all y, f of y is equal to 2y minus 1. Symbolic execution can execute this program and confirm that this is indeed the case, thus performing a more general sort of test. The way that this is possible is that the symbolic executor can run the program to the point that it depends on an unknown, and then it will conceptually fork the symbolic executor to consider all possible values of that unknown that would affect the control flow of the program. So here we see the function f, and we see that it depends on x, its argument, at the first branch. If x was symbolic, as in our assert, then the symbolic executor will consider both branches, that is, the case when x is greater than 0, and the case when it is not greater than 0. And of course, in this example, when it does that, it will discover that the assertion will not hold for non-positive values of x. Let's look at another example just to get a flavor of how symbolic execution works. Of course, we'll go into much greater detail later on. So here on the left, we have a program, and in the program, we've assigned to 3 of the variables, a, b, and c, symbolic values, alpha, beta, and gamma. The rest of the program is a series of conditionals and assignments. At the end, we see an assertion that we would like to hold for all possible runs of the program. Alright, so the symbolic executor will start, and it will execute line 3, initializing x, y, and z to 0. Then it will reach the conditional on line 4. This conditional depends on a symbolic value, alpha, and so it will consider whether both branches are possible, and of course they are. At first it will consider the true branch, that is, when alpha is non-zero. In that case, it will assign x to -2. Then it carries on to executing line 7. Here, the guard depends on a symbolic value again, and so it checks whether beta can be less than 5. Again, it could be or it might not be, so the symbolic executor will pick one direction. Here, suppose that it picks true. Now we see that we'll skip line 8, and the reason is that along this path, we've assumed that a is non-zero, and that means the conditional on line 8 will not hold. After assigning z to 2, we reach the assertion, and we see that the assertion succeeds. And that's because x is -2, z is 2, and y is 0. The sum is 0, and of course 0 is not equal to 3. Now, we can characterize this particular path of our program execution using what's called a path condition. That is, along this path we assume that alpha was true, i.e. non-zero, and beta was less than 5. So we want to also consider the other paths by considering those branches again and going the false direction if possible. So, for example, we could take the false side of the branch on line 7. In that case, we'd skip lines 8 and 9, reach the assertion again. In this case, the assertion is still going to hold because x is -2, the other two are 0, and therefore the resulting sum is not 3. Alright, we'll consider the other branch once again. On this branch, we'll now assume that alpha is false, and we'll check whether b is less than 5. Again, we have no constraints on beta, the symbolic value, so we could go both ways. Suppose we go the false direction this time, thereby skipping lines 8 and 9. Here the path condition is not alpha, that is, we're assuming that alpha is false, and b is greater than or equal to 5. Now we'll go the other direction. In this direction, we're assuming that alpha is not true, and gamma is true. Can this condition hold? Sure, it depends on what c is, and we have not constrained that. That is, we have not constrained gamma. So suppose we go in the false direction. In this case, we'll assign z is 2 because we skipped the assignment to y. However, if we go in the true direction, then y equals 1 and z equals 2, and now the sum of y being 1, z being 2, and x being 0 is 3, and that violates our assertion. Importantly, the assertion violation comes with the path condition, not alpha, and beta is less than 5, and gamma, and this precisely states all of the inputs that will cause this test case to fail. That is, if we used a satisfiability solver to give us a potential solution to this path condition, we could produce a test case that shows the failure. And of course, this is very useful because the developer can then run that test case and use it to diagnose the reason for the failure in the program.
Notice that each path through the tree we just constructed represents a set of possible executions. More precisely, it represents all of those executions whose concrete inputs are solutions to the path condition. This set is a very precise notion of code coverage, viewing symbolic execution as a kind of testing. Complete coverage of the program would be all of its paths. Symbolic execution allows us to systematically consider many of these paths. Viewed as a kind of static analysis, symbolic execution is complete in that whenever a symbolic executor claims to have found a bug, the claim is true. However, it is rarely sound because it is unlikely to cover every path. The reason is that most programs do not have a finite number of paths, and so symbolic execution will not terminate, except by imposing a time limit or other resource limit. Symbolic execution's high precision, the source of its completeness, can be characterized as path, flow, and context sensitivity in static analysis parlance.